Chapter 16, Part 4. So one of the things that makes the Bronsted-Lowry concept of acids useful is that other things can also have acidic and basic properties. And so specifically, specific ions can do this. So an ion can act as an acid if it creates H3O plus in a reaction, or can act as a base if it creates OH in a reaction. So if you have sodium cyanide, when it reacts with water, it's going to completely dissociate. And this solution has a pH of 11.1, so it's a basic solution. So one of these two ions is creating a basic solution. So what we have to assume is that all of these salts, all of these ionic compounds, the ions completely dissociate. They completely break apart in the water. So then we look at them individually to see how each of them interact with water, to see if any of them can create H3O plus or if they create OH minus. So Na is unreactive with water. What's happening is Na is forming NaOH and H+, but this, remember, is a strong base. So then this is going to immediately dissociate back into Na+. So really we're not forming anything. And even though we're forming H+, we're also forming OH-, which combine to form water. The cyanide, however, produces HCN and OH. HCN is a weak acid, which is not going to completely break apart. It's going to stay mostly together. And then it's also going to form this OH- in that reaction, which then is going to create its basic properties. So anytime you react an ion with water, this is called hydrolysis. We want to see what the products are going to be. So typically, anything that has a negative charge, you're going to add hydrogen to it. If it has a positive charge, you're going to add hydroxide to it. That's sort of what the reaction is going to be. So because OH is a product in this case, that is a basic substance, which is why these solutions are basic. So any hydrolysis reaction is going to produce one of two things: conjugate acid and hydroxide. This is going to be a basic reaction. Or conjugate base and hydronium ion, which is going to be an acidic reaction. So in this case, we form a basic reaction because we're forming this OH-. So we can write a Kb for this reaction. Where same things, products over reactants, don't include water. So in this case, we have your ammonium ion. So what it's doing is it's acting as a base, acting as an acid, and donating a hydrogen to this. So one of the products that's formed is your H3O+, which means you have an acidic reaction. So you can write a Ka. So if you have a particular salt, an ionic compound, how can we predict if when it breaks apart into water, if that solution is going to be acidic, basic, or neutral? So what we want to do is look at what it forms when each ion reacts with water, and then compare the strengths of the things that form. So in general, if you have a weak acid, the anion of that is a good proton acceptor. So therefore, anions of weak acids are basic. So that cyanide is an example of that. Same thing holds true for your acids. The cations of weak bases are acidic in nature. So if you have a strong acid, one that donates protons very well, they basically have no basic character. They do not hydrolyze at all. So what that means is that these are neutral. If you have a strong base, it also is not going to hydrolyze, so it's going to also be neutral. So what you do is you look at the individual ions that compose the salt, and you see how each of them interact with water. What products do they form? So in this case, we have potassium acetate. So potassium acetate is going to break apart into K and your acetate. So let's see what happens when we interact both of those with my water. Okay. So remember, water is composed of OH, H being positive, OH being minus. So we can kind of easily see what's going to react with what. The K plus is going to react with the OH. And then the minus is going to react with the H plus. So if we look at my first reaction, potassium hydroxide is a strong base also. So then this is going to break apart and back into K plus and OH minus. These cancel out, so this component is neutral. But here we have a weak acid that's going to stay together. So we have additional OH present in our solution. So overall, we are basic for this salt. So in general, these are your rules. If you have a strong base and a strong acid that forms from your ions, then you have a neutral solution. There's nothing that's going to form H pluses or OH minuses. If you have a strong base with a weak acid, then it's going to give a basic solution. Which makes sense, give a strong base. If you have a weak base and a strong acid, your solution is going to end up having an acidic solution. If you have a weak base and a weak acid as the two products, you have to figure out which one of those takes precedence. So you do that by comparing the two K values, Ka versus Kb. If the Ka is larger, it's acidic. If the Kb is larger, then it's basic. So first thing I want to do is run through your list of strong acids and strong bases, because it's a good idea to have sort of a general list so you know what is considered strong versus weak. So I'm going to pause and write them down, and then you should. So here's your list of strong acids and strong bases. So your 6 acids that are considered to be the strong ones. So if it's not on the list, you consider to be a weak acid. And then your strong bases. So the first 4 are OH combined with elements in group 1 of the periodic table. And then your ones for group 2 also are those as well. MgOH is not considered one, so it starts with calcium, strontium, barium, and also probably lithium hydroxide. That's another group 1. All of those are considered to be strong. All right, so let's say we have K2SO4. So this is going to break apart, first of all, into K and SO4. So let's see how each of those interact with water. KOH plus H plus. So let's look at what we form. We form a strong base and a strong base and a strong acid. Strong base and strong acid means overall it's neutral. Zinc nitrate is going to form zinc and nitrate. Same thing, react both of them with water. Okay, so the two things we form, this is a weak base, this is a strong acid. So a weak base and a strong acid is going to be acidic. Na2S is going to be Na and sulfide. I'm sorry, I lied for this first one. H plus, this is OH minus. So we form a strong base and a weak acid. So strong base is going to take precedence. This solution is going to be basic. So it's kind of a good way to tell what is going to form. Let's say you want to calculate the pH. So what you have to do is be able to relate Kas and Kb's because Kas and Kb's are only for acids and bases, not the conjugate acids and conjugate bases. But those two quantities are related to each other through this reaction here. The Ka for a substance times the Kb is equal to the K of water, which is 1 times 10 to the negative 14th. So if you can know one of them, you can figure out the other. Okay. So if only one ion hydrolyzes, then you have to, or you have a weak acid or a weak base, you would have to do an icebox to figure out the amount of H plus or OH minus that you have present to then figure out the pH. Okay. The only difference between these is that you have to do one extra step to figure out the appropriate K value to use. Okay. So we have an NaCN solution. What's the pH? Okay. So if we were to look at this, okay, Na plus water is going to form NaOH and H plus. NaOH is then going to break apart. So there's no reaction that happens. But CN plus water does have a reaction. It forms HCN plus OH minus. Okay, so that's the reaction we care about. Okay, so first of all, what we have to do is we have to figure out the Kb, because this is a basic reaction, because we are forming hydroxide. And we can do that from the Ka. So our Ka times our Kb is equal to our Kw. So in this case, our Kb so our icebox is the same as before. Our solution is 0.100. And we continue to solve the exact same way. So our K expression is going to be Kb x squared minus x. We can check to see if our simplification works by seeing if 0.1 over our Kb is greater than 100, and yes it is. So then we can solve for our OH amount by plugging in our Kb value. This is equal to 2.04 times 10 to the negative fifth. So when we solve for x, you get a value of 1.43 times 10 to the negative third. X in this case is our OH. So what we first have to do is find our POH. And then we can find our pH because those two are related. And then check to see if it makes sense. We know that this should be a basic reaction because we have a Kb, and our pH does signify that this is a basic solution, 11.16 greater than 7.